Hello everyone, this video is an in-depth exploration of flying wings, primarily focusing on their design, also reviewing their performance and stability characteristics. A bit of my background first for whatever credibility it gives me here. I'm a 23-year-old working aerospace engineer, and I studied mechanical and aerospace engineering in my undergrad. Right now, I'm working through my master's in aero, but I've always been a big aerodynamics guy and an aerodynamics nerd, and I've been consistently designing and testing more unorthodox aircraft models for years. I've had a few other engineers mention that it would be cool to document my notes for my most recent projects here in a video format, so I guess that's what this video is. One of my most recent home projects has been designing and flying a tailless aircraft or a flying wing. I've always been a big fan of the careful and elegant design of these vehicles, and I really just wanted to challenge myself to design one from scratch and fly it. So in this video, I'll be diving into the performance and stability characteristics of tailless aircraft and their components, as well as the mathematical design theory and principles responsible for getting one of these in the air. Real quick, as I walk through my notes here, I assume whoever is watching has at least a fundamental understanding of multivariable calc and low-speed aerodynamics. So what exactly is a flying wing, and how do they differ from traditional aircraft? Flying wings are exactly what they sound like, a flying wing and just a flying wing. When most engineers hear this, they immediately think B-2 Spirit bomber and have probably seen the viral image comparison between a Peregrine Falcon in flight with the bomber. These aircraft obviously have no traditional tail and are usually characterized by a high sweep, taper, and a low profile. I won't go deep into the history behind this configuration, but here's what it's important. A pure flying wing is theoretically the lowest drag configuration for a fixed-wing aircraft. Without a tail or significant fuselage present, the viscous drag of the aircraft is decreased, meaning that the aerodynamic efficiency, which is just the lift-to-drag ratio, is much higher than that of the same aircraft with a tail on it. Ultimately, this uses less power and fuel to go the same distance as the tailed aircraft. Besides drag, the weight reduction of removing the tail assembly means that the aircraft has a lower wing loading, which in turn means that the bending moment on the wing is decreased, which in turn means that there's a decrease for requirement in the minimum weight of the aircraft's internal structure that's required to maintain the structural integrity in flight. With no vertical surfaces present, flying wings have an incredibly low radar cross-section, making them fantastic for stealth purposes. So that's why today's stealthiest aircraft like the B-2, the B-21, the X-47 UCAS, and the new XRQ-73 are often tailless and flying wings. If these can be so efficient, why don't we see more of these? There are a few reasons. So remember that pure efficiency isn't everything in aircraft design. The aircraft must also be practical in numerous aspects. A good example of this is commercial flight. The best shape for a pressure vessel or plane at high altitude is a tube or a cylinder. And a flying wing is not quite as well suited to perform as a pressure vessel compared to a tube commercial cabin. Also, imagine sitting 30 yards from the center of the aircraft in a banking turn. I'm not sure that would be too fun. Another reason why we don't see these in commercial aviation is that it's much more difficult to upgrade or modify an aircraft that's one big contoured wing than an aircraft that has separately defined components like wings, winglets, the fuselage, and tails that can each be modified individually. Aerodynamically, flying wings often need special airfoils or wing twists, or a combination of both, which creates more trim drag and can end up sacrificing lift for stability. And because there's no horizontal or vertical stabilizers here, pitching and yawing stability must be achieved aerodynamically or forced through control surface actuation like in elevons, rather than geometrically simply by a tail far from the CG. Because the control and stability characteristics here differ from traditional aircraft designs, the design for stable and controllable takeoffs and landings can be challenging, and it can be particularly difficult to decouple any yaw roll or Dutch roll coupling or roll pitch coupling for tailless aircraft, especially in those without a fin. Real quickly, let's define a few key terms. The center of pressure, the CP, is the point along the chord where the sum of the pressure field acts on a body. And the pressure field changes as the angle of attack, or alpha, changes, so the CP location is dynamic and dependent on alpha, whereas the aerodynamic center, which is the AC, is the point along the chord at which a pitching moment is independent of alpha. And thin airfoil theory derives this point as approximately a quarter chord for most subsonic airfoils. But importantly, the AC location is independent of alpha. And another useful definition is the neutral point, which is the station where the CG placement causes neutral stability in an airfoil or wing. For an airfoil, the neutral point and aerodynamic center are synonymous. Now, knowing the theory behind static stability, let's walk through how this applies to an aircraft specifically without a tail. Let's start first with longitudinal or pitching stability, considering a generic lifting airfoil with positive camber. In the reference frame of the wing, an airfoil will generate a normal and axial force, which can be translated to the wind reference frame with simple trig. The vector sum of the lift and drag vectors produced by the foil are denoted here by R. By convention, we refer to the positive pitching moment of the foil as a nose-up rotation by the CG, and for the static stability of an infinite span wing of this airfoil cross-section, the condition for longitudinal stability is satisfied when the rate of change of the pitching moment coefficient with respect to the rate of change of the coefficient of lift is negative, meaning that the aerodynamic center is further aft than the CG. Graphically, this is just a negative slope on the plot. Now, the equation here is just a version of the neutral point equation for longitudinal stability without the tail terms. If we follow the assumption that for low alpha angles, CL is proportional to alpha, this equation is a bit easier to visualize. This is a simple derivation for the definition of the neutral point as the location at which the CG placement causes neutral stability, which again is synonymous with the AC for an airfoil. This relationship basically tells us that the CG must be forward of the AC of an airfoil for flight, but still does not guarantee a stable gliding flight. We can also derive a slightly more practical relationship between the pitching moment and the rate of change of the chordwise station of the center of pressure with respect to the rate of change of alpha. And breaking down the airfoil's moment around the aerodynamic center into its components with the resultant aerodynamic vector, and then using the product rule, if all the moments are assumed to be acting at the aerodynamic center, then x is effectively 0 because we're now considering the moments in the frame of reference of the aerodynamic center itself. And that simplifies the equation to this. Now remember that for restorative stability, we want negative or nose-heavy pitching moments. So with this equation, longitudinal stability depends on the sign of dx over dA, and the margin of this stability depends on its magnitude. If you really think about it, the right side of this equation just represents the travel of the center of pressure of the airfoil as alpha increases. Now as the CP moves forward, the dx d alpha term turns negative, and the dm d alpha becomes positive, which is not stable. For positive static stability, this airfoil, the CP movement should be aft. All positively cambered and high lift producing airfoils experience a less than 0 dxda, or the CP moving forward when alpha increases. And this is exactly why planes with these wings require a tailplane for stability. So with this knowledge, let's more specifically hone in on how to achieve stability without a tailplane while still generating positive lift in the case of a tailless aircraft or flying wing. Now let's consider another wing of infinite span, this time defined by a symmetrical or uncambered airfoil with the CG placed exactly at the AC. We can say that with this definition, at alpha equals 0, the pitching moment coefficient also equals 0. If we consider now a positively cambered airfoil, the moment coefficient will be negative, indicating a nose-heavy moment generated by the pressure distribution between the upper and lower surfaces. To balance this wing at 0 alpha, the CG must be behind the AC. This sounds super weird. That's because it is. This is ignoring any alpha effects of CP travel. And let's remember that the simplified equation for static stability is here. So this airfoil can be stable in a static condition in the image, but will be unstable to any other mode of flight, any pitch disturbances. If we now take the trailing edge of this and bend it upward slightly, we have what's called a reflexed airfoil. And these are characterized by their positive pitching moment coefficient. Placing the CG forward of the AC in this airfoil results in a wing that is stable to pitch disturbances. And a reflex type wing offers better low speed characteristics than that of a symmetrical airfoil for the same flying wing application. And that's primarily thanks to the positively cambered leading edge. There are two major common approaches to overcoming this instability. And number one is to generate the stabilizing pitching moment in the wing itself. To make this a little bit more intuitive, I ran a linear VLM analysis on a rectangular wing of a unit chord length for the profiles that we just mentioned, one symmetric profile, one cambered profile, and one reflex profile. By the slope of the plot on the left, we can verify that our assumptions in the thin airfoil theory hold true, as the neutral point is exactly at the quarter chord station. And we can see by the plot on the right that for the symmetric airfoil, our pitching moment is 0 at 0 alpha. Similarly, a positive cambered airfoil returns the same exact AC station, but what's different here is that at 0 pitching moment, the airfoil generates negative lift, and at 0 lift, the pitching moment is negative or nose heavy, like we checked out earlier. Now, considering the wing with the reflexed airfoil, we see the same aerodynamic center station as we would expect to, but now notice how the 0 lift pitching moment is positive, and the lift generated at the 0 pitching moment alpha is greater than 0. The singularities in this plot are the 0 pitching moment alphas, and we can see for the wing with the positively cambered NACA 4415 airfoil that the CP moves forward as alpha increases, whereas for the wing with the reflexed MH61 airfoil, the CP moves aft with alpha. This brings us all the way back to a solution to the longitudinal static stability equation we derived earlier, which requires that dx d alpha is negative. But let's not forget that we are trying to simply make dx over d alpha greater than 0, which means the CP moves aft as alpha increases, not considering any other stability derivatives or their effects right now. To counteract the negative dx over d alpha generated by a positively cambered airfoil on a wing, you can add a tail to the aft of the aircraft, and that would counteract destabilizing moments. Or you can also add a tail to the front of the aircraft, which is called a canard. But we aren't interested in tails here, so how else can we replace the stabilizing moment generated by the tail? So why don't all planes use a reflexed airfoil in their wings? Well, first of all, the reflexed trailing edge intends to balance the lift produced by the front of the foil and the leading edge, and the overall loss of lift can be anywhere from 9 to 16% approximately compared to identical airfoils with no reflex at the trailing edge. And it's also said that reflexed airfoils experience a slightly higher profile drag. The lesson here is that pitching stability can't be gained easily without the loss of lift. And the second common approach to overcoming instability here is with wing twist, or commonly known as washout. Washout is effectively putting a little bit of tail at the end of the wing itself. With wing twist like this reduces the wingtip vortex and the associated induced drag at the cost of a lift distribution reduction across the span. We'll take a look at this lift distribution in a minute. But with washout, we can also improve lateral stability, or the yawing moment, which will be especially important at low Reynolds numbers and high angles of attack here. Washout also delays the onset of stall at the wingtips, which means that the aileron or elevon control authority can still be maintained when the root of the wing is stalled at higher AOAs. Swept wings in this application tend to stall at the wingtips first due to the lateral boundary layer flow, so the washout in coupling with this can reduce or eliminate this. With washout, as alpha increases, the lift at the wingtips becomes positive or increasingly positive. So considering a wing with just sweep, the wingtip moment arm about the pitching axis is significant for stability. If a swept wing has some washout included, the wingtips generating high lift compared to the stalling wing root will push the nose back down, just like a traditional horizontal stabilizer or tail does. There are two methods to producing the washout effect in a wing, number one being geometric twist and number two being aerodynamic twist. Geometric twist is where the root and the wingtip are the same airfoil, while the wingtip airfoil is set at an angle of incidence several degrees below the root, and this produces significantly more drag than the alternative aerodynamic twist does. Aerodynamic twist is replicating the effect of the geometric washout or geometric twist by using a different tip airfoil than the root airfoil, and the tip airfoil having little to no negative twist. If we select airfoils with different zero lift angles, we can reduce the amount of geometric twist needed here. And the difference between the zero lift angles in the airfoils is called aerodynamic twist. And we need to study the airfoil polars to find these angles. Also, a small negative or even positive moment coefficient in the tip airfoil reduces the required amount of geometric twist and improves the overall design performance of the wing. Dr. Pegnan derived the formula presented here, which is important in that it provides early in the design process a well-tested method of determining the geometric twist required for stable flight. This methodology provides only the total twist required for longitudinal stability for a given monolithic wing with a straight leading edge and straight trailing edges. and a predetermined static margin. The computed twist values have also been proven in practice to be extremely accurate for the sweep angles up to 30 degrees for tapered or constant chord wings. This methodology was also implemented into some of the theory used in this quick design spreadsheet that I made, which basically takes a few inputs like weight, velocity, sweep, taper, and the root and tip airfoil polars, specifically their zero lift angles, and returns the necessary geometric twist for a basic flying wing of a predetermined CL and static margin. It's also important to discuss the effect that the wing's twist has on its lift distribution. There are two primary lift distributions that I'd like to discuss here, one being the elliptical and one being the bell-shaped. The elliptical lift distribution is a concept in aerodynamics where the lift generated along the span of the wing is distributed in an elliptical manner. The distribution is considered ideal because it minimizes the induced drag generated, and in an elliptical distribution, the lift per unit span decreases smoothly from the root to the tip, forming an elliptical shape when graphed. This elliptical lift distribution is known for producing the minimum possible induced drag for a given span and total lift, and it's also known for the even downwash generated, and the uniformity of this downwash contributes to the efficiency and the reduced drag of the wing. In practical terms, wings designed with an elliptical lift distribution tend to have higher efficiency and performance due to the reduced induced drag. This principle was famously applied in the design of the Spitfire's elliptical wing, which contributes to its exceptional performance in World War II. Achieving an exact elliptical lift distribution in practice can be complex due to structural and manufacturing constraints, but understanding and approximating this distribution remains a fundamental aspect of aerodynamic wing design. Pivoting to a more structural approach, if you held the structural weight and root bending moment in the wing as constants, is there an alternate lift distribution that yields lower induced drag than the elliptical lift distribution does? It turns out that there is. In 1933, Prandtl published a paper presenting a superior span load than his previously published elliptical lift distribution, and this was called the bell-shaped lift distribution. This has the lowest aerodynamic drag for a given lift and bending moment in a wing. He published his theory in a German soaring magazine, but it was never really translated into English, and it was largely forgotten by most of the aerodynamics world. With the bell-shaped distribution, the vortices are purposely located inside the span rather than at the tips, and this causes the tip to experience an upwash, which then causes the wing to have an induced thrust at the tip, as the airfoil resultant vector is leaned forward. Like we just reviewed with the elliptical distribution, you strive for an even downwash behind the wing, but here, this downwash becomes upwash at a point somewhere around 70% semi-span. And when an aileron or elevon is depressed for a roll control, it deflects downwards into upwash, reducing drag and producing Proverse Yaw. Normally, a downside aileron is in downwash, increasing drag and adverse yaw. This also means that you can retain roll control during and after a stall event, and this greatly reduces spin tendencies via the unloaded wingtips. This induced thrust helps to achieve Proverse Yaw, and it was proven in 2015 by aerodynamicist Al Bowers. And this means that when you roll rightwards with a wing of this lift distribution, you also yaw rightwards, and this eliminates the need for vertical tail and rolls, and is exactly why birds don't have vertical tails. And to summarize the effects of wing twist, particularly in a tailless aircraft, wing twist decreases the max CL and lift distribution over the wing surface, as well as decreases the overall drag. This is primarily due to the wingtip vortex reduction. It also improves yaw stability and delays stall onset of the tips. And with a combination of sweep and twist, the lift-producing wingtips at the root stall alpha have a large moment arm on the CG, and this just means a strong stall recovery. Now, you'll also notice in many of these flying wings that there's often taper from the wing root to the wingtip. What is taper and why is it used here? The primary advantage of adding a taper ratio to a wing is the reduction of induced drag. Tapered wings distribute lift more evenly across their span, which reduces the intensity of the wingtip vortices. The magnitude of this vortex is directly proportional to the pressure difference between the high pressure and low pressure regions on the wing, so by tapering this wing, the lift distribution becomes more gradual towards the wingtips. Aerodynamically, wingtips are the least efficient region of the wing, generating the most drag for the least amount of lift, especially without winglets or end plates present. Tapering wings biases the lift and drag towards the wing root, and minimizes the bending moments and allows for a lighter wing spar. Structurally, this keeps the lift-generated bending moment relatively constant across the span, which decreases the structural requirements of an equivalent rectangular wing at the cost of slightly lower lift. From a performance standpoint, tapered wings also allow for better performance at higher speeds due to the leading edge sweep, which can delay shockwave formation and reduce wave drag at transonic speeds. Additionally, they can improve roll performance by producing an effective dihedral. Reducing the wingtip loading and wingtip mass result in a lower roll inertia, and this makes the aircraft more responsive to aileron inputs and reduces the tendency to roll in response to side slip. Historically, the Horton flying wings utilized a highly tapered wing with a bell-shaped lift distribution over the span, which produced a small downforce at the tips. This ultimately reduced adverse yaw and allowed them to fly without a vertical tail, and achieving this lift distribution required extensive washout, sometimes up to 8 degrees, which we reviewed a couple minutes ago. Now, as cool as a tapered wing looks, there are downsides to this. The primary drawback of low taper ratios is that the tip sections operate at a lower Reynolds number than the root sections, meaning that at high AOAs, the tip sections are more likely to stall before the root sections are. Again, a stalled tip causes the aircraft to roll and lose lift simultaneously, which leads to a nose-down pitch, which is a classic symptom of entering a spin. The stalled tip flow also reduces aileron effectiveness like we looked at earlier, making it harder for a pilot to lift the drooping wing and prevent the roll and ultimately the entrance into a spin. Now, to counter these stall and spin problems, several solutions can be implemented here. First of all, the designer can progressively twist the wing section profile so the tip sections are flying at the lower incidence than the root. We reviewed this in the washout or twist section of this video. You can also gradually change the section profile so that the tip section has a different thickness and camber compared to the inboard sections, which ultimately delays the wing incidence at which the tips stall. Again, this is just called aerodynamic twist. And lastly, the designer can also introduce stall trip devices to the wing root sections, such as increasing the nose profile or adding stall or trip strips. The primary function of these is to initiate flow separation in the upper surface of the wing during flight at high AOAs. And this can help to create a more controlled stall across the wing and prevent entrance into a spin. This also improves the overall controllability of the aircraft approaching stall. With a tapered wing, the more complex shape also increases the manufacturing complexity, particularly with sheet metal. Modern composites have mitigated some of these issues, but the shape can still be challenging to make. For most applications, a tapered wing is ultimately chosen for its higher performance or load capability, despite the more demanding handling at high angles of attack. So, not realizing I was already at 23 minutes here and I still have quite a few notes left on the topic, I think I'll push a couple of these topics to the next video, these being static and dynamic stability and modes, and which of these are specifically important to flying wings, and then a deep dive into stability derivatives and which ones are more important and less important for flying wings, and then taking all of these principles and theories and tying them up and implementing them into a design of a flying wing, and along with that, the analysis of that aircraft and ultimately the test of that aircraft.